Hey everyone, welcome back for another deep dive. Today we'll be looking at something that seems pretty simple at first glance, a sequence of numbers. But trust me, this one goes deep. We're talking about the A000016 integer sequence. You ready to decode some math secrets with me?
Absolutely. It really is fascinating how the sequence connects some pretty different mathematical concepts. And it all starts with this string of numbers: 1, 1, 2, 2, 4, 6, 10. Do you see any patterns there?
Well, I'm seeing some doubles in there, like the 1, 1 and the 2, 2, but I can't quite figure out the rule yet.
Okay, think of it this way. Imagine you have a row of light switches. Each switch can be either on or off, representing a 1 or a 0. They're wired in a way where they flip on or off based on what the switches before them are doing, like some kind of chain reaction. Each switch is affected by the ones that came before it. This setup is called a shift register, and our friend A000016 tells us how many unique patterns those light switches can make.
Oh, so it's not just a random list of numbers. It's actually describing how these shift registers behave. That's pretty cool.
Yeah, exactly. And to help us with our deep dive, we're going to be using a couple of sources. We have the Online Encyclopedia of Integer Sequences, or OEIS, which is like our dictionary for all things integer sequences. Then we've got some excerpts from the Encyclopedia of Mathematics to help explain these shift registers. And to add another layer of intrigue, we've even got some historical notes that we'll be referencing.
Okay, I'm ready to dive in. So let's get specific. What exactly is A000016 telling us about these shift registers?
So A00000016 represents the number of distinct output sequences from what's called a binary end-stage shift register. These shift registers are special because they have this feedback mechanism where the last switch actually affects the first one, creating a continuous loop. And the N refers to the number of switches or stages that are in the register.
Okay, so if I have like 3 light switches in my shift register, A000006 will tell me how many different patterns I can get when those switches flip on and off.
Exactly. And the OEIS even gives us an example for a three-stage shift register. It shows that there are only two possible distinct output sequences: 0001100101 and 010101. See how they repeat? These repeating patterns are a key characteristic of these outputs.
Okay, yeah, I'm starting to see the picture. But this is where it gets a bit confusing. The OEIS also gives some other definitions for A000016. Like it mentions something about binary necklaces with an odd number of zeros. What does that even mean?
Ah, that's where it gets fun. It might seem like we're jumping from light switches to jewelry, but there's a connection here. Imagine taking that string of zeros and ones from the shift register output and you bend it into a circle like a necklace. Each 0 or 1 becomes a bead on that necklace.
Okay, I can visualize that.
Yeah.
So these binary necklaces are just another way to represent the output of the shift register.
Got it. And the odd number of zeros part just means that we're only looking at necklaces that have an odd number of zero beads. The cool thing is that the number of these unique necklaces with an odd number of zeros also matches up with our A000016 sequence.
So we're seeing this one sequence, A00000007, popping up in these different places that don't seem related at all. It's like a code that unlocks all these mathematical concepts.
Precisely. And that's just the beginning. Remember those historical notes we talked about? They mention that shift registers have been used in all sorts of things, from cryptography to communication systems. And to design and analyze those systems, we need to understand the properties of A00000007.
Okay, now I'm really interested. So this sequence that seems so simple is connected to some pretty complex technology. Can you tell me a bit more about how these shift registers actually work?
Sure. So these shift registers aren't just a bunch of light switches. They have some important parts that make them function. The Encyclopedia of Mathematics gives a good explanation of these components. We've got the cells, which are like our individual, switches a clock that controls when they flip the shifting action that moves the bits from one cell to the next, and a feedback function that determines how the output loops back to the start.
It's like this carefully choreographed dance of zixins and ones happening inside.
That's a great way to put it. And A000016 is all about figuring out how many different dances are possible given a certain number of dancers or stages in our shift register.
Okay, that makes sense. So we've got these shift registers making these sequences, and A000016 is keeping track of all the unique patterns we can get, but I'm still not sure how any of this actually applies in the real world.
Well, just think about all the times you come across randomness in technology, like shuffling songs on a playlist or generating characters in a video game, or even when you're encrypting sensitive information. Randomness is essential. And you know what? Shift registers are actually really good at creating something called pseudo-random numbers.
Pseudo-random, so not actually random.
Yeah,
Is that like those magic tricks where they say it's random, but they're actually controlling everything?
you're on the right track. True randomness is actually pretty hard to find in the digital world. Computers follow instructions step by step, but we can design them to create sequences that look random even though they're based on rules. That's where shift registers come in.
Okay, so these shift registers can make numbers that seem random enough for most purposes, but how does that connect to our A000001 seed sequence again?
Remember, A000000 tells us how many unique sequences a specific shift register can make. When we're talking about generating pseudo-random numbers, we want ones that can make really long sequences before they start repeating. The more unique sequences a shift register can make, the more random its output will seem.
So a higher number for A000000 SOR means you have a better pseudo-random number generator. It's like having a deck of cards with more cards in it. You're less likely to get the same hand over and over.
That's a great way to think about it. But it's not just about the quantity, it's also about the quality of the sequences. We want sequences that actually pass statistical tests for randomness, so we know they behave like truly random numbers.
So not all shift registers are created equal when it comes to this pseudo-random number stuff.
Exactly. And our historical notes mention that researchers have spent a lot of time trying to figure out which shift registers make the most random-looking sequences. They've been looking at different feedback connections and setups to try and find the best ones.
It's like tuning a musical instrument to get just the right sound. You have to adjust the settings to get what you want.
Precisely. And knowing about A000016 can help guide us to pick the right shift register for the job. It lets us predict how long and how random the sequences it makes will be.
Okay, I get it. So shift registers are used to generate these pseudo-random numbers, and those are used in all kinds of applications. But I'm still curious about those historical notes that talked about cryptography.
Yeah.
How do shift registers fit into that world of secret codes and ciphers?
That's where things get even more interesting. One way they've been used in cryptography is with something called stream ciphers. Imagine you want to send a secret message. A stream cipher takes your message and combines it with a pseudo-random key stream, which is like a secret code. This creates an encrypted ciphertext.
So it's like you're taking your message and scrambling it up using this random sequence of characters.
Exactly. And guess where that random sequence comes from? You got a shift register. And the randomness of that key stream that's created by the shift register is what makes the encryption secure.
But wouldn't someone who knows how the shift register works be able to figure out the key stream and break the code?
That's a great question. And that's why choosing the right shift register and its feedback function is so important for keeping things secure. If someone knows how the shift register is designed, they might be able to predict what it will do and break the encryption.
So it's like this back and forth between cryptographers who are trying to create unbreakable shift registers and code breakers who are trying to crack them.
That's the game. And this is where understanding A000016 gets even more crucial. Knowing about this sequence helps cryptographers design systems that are more secure by making sure their shift registers create highly random sequences.
Wow, my mind is blown. This sequence of numbers that seems so simple is actually connected to all this high-stakes stuff. But I'm guessing this isn't the only thing shift registers are used for, right?
Nope, you're absolutely right. They also play a big part in communication systems, especially in something called spread spectrum communication. Imagine trying to send a radio signal over a channel that's full of noise. Spread spectrum techniques spread the signal across a wider range of frequencies, making it less likely to be disrupted by interference.
So instead of sending the signal on one frequency, you're sending it on multiple ones at the same time.
Exactly. And guess what's used to create those spreading codes? Yep, you guessed it, shift registers.
These shift registers are like the multi-tool of technology.
I like that analogy. And just like with the pseudo-random number stuff, understanding A000016 helps us choose the right shift register for creating good spreading codes.
So A00000016 isn't just some abstract mathematical idea. It's actually a key part of understanding how these technologies work and how to improve them.
Precisely. And that's one of the coolest things about studying integer sequences. They often show us these unexpected connections between different areas of math and technology.
Well, I'm hooked now. I can't wait to learn more about this A000001 sequence and see what other surprises it has in store. What should we look at next?
Let's revisit those alternative definitions we mentioned earlier, like the ones about binary necklaces and subsets of numbers that add up to 000016. We might find even more insights into the nature of A000016 by looking at those in more detail.
Yeah, those alternative definitions are pretty interesting, like the one about binary necklaces. Remember we talked about visualizing the shift register outputs as circles? Those are our binary necklaces. It's like a string of beads, and each bead can be either black or white, representing a 0 or a 1. Binary necklace is just a unique arrangement of those beads in a circle.
Okay, I remember that. But what's so special about these binary necklaces that have an odd number of zeros? How does that relate back to A000016? Well, that's where things get a little bit wild. The OEIS tells us that A000006 also counts the number of these special binary necklaces that have an odd number of zero beads. So it's like saying that the same sequence that describes the number of distinct outputs from a shift register also describes the number of these unique necklaces.
Whoa, hold on. So there's this hidden connection between the outputs of a shift register and these binary necklaces that seem totally different. It's like finding a secret passage that connects two different rooms.
That's a great way to think about it. It shows that there's a deeper mathematical link here that goes beyond just shift registers and into other parts of math.
Okay, my brain is starting to hurt. But what about that other definition, the one about subsets of numbers that add up to 0 modulo n? That one still sounds like a mystery to me.
Let's try and break it down. It's basically about finding groups of numbers from a set where if you add them up and divide by n, there's no remainder. For example, if n is 5, we're looking for groups of numbers from the set 1, 2, 3, 4 that add up to a multiple of 5.
So like 3 and 2 would work because they add up to 5, which is a multiple of 5.
Right. Exactly. And the surprising thing is that the number of these unique groups of numbers or subsets is also given by our friend A000016.
So we have the shift register outputs, the binary necklaces, and now these special groups of numbers all connected by this one sequence. It's like A00000016 is a language that all these different mathematical ideas can understand.
That's a great way to put it. We're seeing how this one sequence brings together these seemingly unrelated concepts, which hints at a deeper structure underneath it all.
I'm starting to see how vast this A00000016 sequence really is. It's not just about counting things. It's about showing us hidden connections and patterns in math.
Exactly. It's like having this key that unlocks different doors, each leading to new and interesting rooms in this giant mathematical world. And who knows what other secrets we might find as we keep exploring this sequence and all its properties.
Well, I'm definitely feeling inspired to learn more about these integer sequences. This deep dive has opened my eyes to a whole new world.
It's been great exploring this with you. And remember, this is just one sequence out of so many others, each with its own unique story to tell. So keep exploring, keep asking questions, and you never know what mathematical treasures you'll find.
Thanks for joining us on this deep dive into the world of A00000016. Until next time, keep those minds curious and keep those light bulbs shining bright.
Welcome back. It's been quite the journey with this A00000016 sequence, hasn't it?
It really has.
Yeah.
We started with what seemed like some simple patterns and ended up talking about pseudo-random numbers and even cryptography.
It just goes to show how connected math really is. And remember those other definitions from the OEIS, the ones about binary necklaces and those sets of numbers? Let's go back to those for a minute because they might have some more insights for us.
Okay, remind me again about those binary necklaces. What was that all about?
Remember how we talked about visualizing those shift register outputs as circles? Well, those are our binary necklaces. Each bead on the necklace can be either black or white, representing a 0 or a 1. It's just a unique arrangement of those beads in a circle.
Right, I remember now. But what's so special about the ones that have an odd number of zeros? Why is that connected to A000000?
Here's the interesting part. The OEIS says that A000000 also counts how many of these unique binary necklaces exist with an odd number of zero beads. So basically the same sequence that describes how many different outputs you can get from a shift register also describes how many of these unique necklaces there are.
Hold on, so you're saying there's this hidden connection between what a shift register puts out and these necklaces that seem totally different. It's like finding a secret tunnel that connects two places you wouldn't expect.
Exactly. It shows that there's something deeper going on mathematically that goes beyond just shift registers and connects to other areas of math.
Okay, my head is spinning. But what about that other definition with the subsets of numbers that add up to A0 modulo n? I'm still lost on that one.
Let's break it down. So it's all about finding groups of numbers from a set, and when you add them up and divide by n, there's nothing left over, no remainder. For example, if n is 5, then we're looking for groups of numbers from the set 1, 2, 3, 4 that add up to a multiple of 5.
Okay, so like 3 and 2 would work because they add up to 5, which is a multiple of 5.
You got it. And the surprising thing is that the number of these special groups of numbers or subsets is also given by A000001
So we have the shift register outputs, those binary necklaces, and now these groups of numbers all tied together by this one sequence.
Yeah.
It's like A000001 is some kind of universal language that all these different mathematical ideas can understand.
That's a great way to look at it. We're seeing how this single sequence unites these seemingly separate ideas, and that hints at some deeper structure behind everything.
I'm starting to get a sense of just how big and important this A00000001 sequence really is. It's not just about counting things, it's about uncovering these hidden connections and patterns in the world of mathematics.
Exactly. It's like having a key that unlocks all these different doors leading to new and fascinating rooms in this huge mansion of mathematical knowledge. And who knows what other secrets we might find as we keep digging into this sequence and what it can do.
Well, I'm feeling pretty inspired to learn more about these integer sequences. This deep dive has really opened my eyes to something new.
It's been a pleasure exploring this with you. And remember, this is just one sequence out of countless others. Each one has its own unique story to tell. So keep exploring, keep asking questions, and who knows what mathematical treasures you might stumble upon.
Thanks for joining us on this deep dive into the world of A000016. Until next time, stay curious and keep those minds sharp.